So, good evening, everyone. I welcome you all to NPTEL course Energy Conservation and Waste Heat Recovery, live session number 10 for week 10. As you all aware that every week on Friday from 7 to 9 p.m. we are having a live session. So, in this live session, we are doing some sample assignment problems based on previous year questions. So, I think these are very helpful to you, and we also revise some concept from the previous week. So let's wait for another 5 minutes. After that, I will start. As of now, we have covered up to 9 weeks. Okay, and all the recordings and all the PPTs, I think, have been provided to you from the NPTEL team. So those who were not able to join the live session, maybe they can see the video on YouTube, or they can access the this PPT that we are sharing here on Google Drive. Just wait for few minutes. After that, we will start. I think my pointer is visible to you. If you are facing any issue in sound, pointer or PPT, let me know. Good evening, sir. Yeah, good evening, Savas. Okay, I think we have enough waited. So let's start with today's class. So the first question is, what is the main objective of energy storage? So in last week, we have covered different type of energy storage. Okay, so we have seen like we are having surplus demand, and sometimes we are not having enough demand and we are having surplus energy. So that's why we have to store energy so that in the time of surplus demand we can supply the energy, and in the time of surplus energy we can store that energy. So that's why energy storage is very important. Okay. So what is the main objective of energy storage? So you have to identify that. Option A is offset adverse effect of fluctuating demand, assure steady output from existing plant, and meet peak demand on short notice. And D, all of the above. So take 2 minutes and think about it and let me know the answer. Sabaz, what do you think about this question? What is the answer?
Sir, all of the above, sir.
Okay. So do you want to explain your reasoning behind option A, B, and C?
No, sir.
Sorry.
Sir, you explained very nicely, sir. You explained.
Yeah. Maybe you can also put your thoughts. No issue.
I actually last week I didn't attended the classes, sir. Last week.
O- Okay. No issue. No issue. So basically, as I have already told, energy storage. So basically, we are storing the energy. Okay. So suppose we are having a power plant of like 100 kilowatt, or suppose 1 megawatt. Okay. So this power plant can operate on 1 megawatt capacity. But as we all aware that the this power plant is supplying the energy to a nearby village or nearby town. Okay. So in that town, you know that during night everyone is sleeping. Okay, so nobody is using any appliances, or like basically they are just using air conditioner, or like in normal condition only the fan, ceiling fan. Okay. But during daytime everyone is working, so the offices are also running, so there are different types of equipments are running everywhere. So basically in daytime the demand is uh, very high as compared to the night time. So daytime the demand will increase. So during day demand is high, and during night demand is low. Okay. But our power plant is having capacity of 1 megawatt, so we have designed our power plant for 1 megawatt. If suppose we are operating our power plant like differentially for day or night, so maybe we can operate for during daytime for 1 megawatt capacity, and during night for 400 kilowatt capacity. So but the equipments and the systems are designed for 1 megawatt, so they will work efficiently if they are operating at their design capacity. If we are not operating the equipments on the design capacity, then the efficiency will be low as compared to the desired efficiency. Okay. So basically we are occurring losses here, and any company don't want to get loss, and we are also and due to the less efficiency we are also polluting the environment. So what we will do here, so we will store energy. Okay. So we will operate our power plant, suppose on an average of maybe 900 kilowatt or 800 kilowatt capacity. Okay. So we will find an optimum capacity. At that capacity I think our power plant is having maximum efficiency, so most of the time we will operate our power plant at that capacity only, and in the event of low energy demand we will store the surplus energy. Okay. And when the edge demand is more, then we will use the stored energy to supply to the town. Okay. So in this way we will maintain our supply. So that is the main objective of energy storage. So option A is offset adverse effect of fluctuating demand. So yeah, we are offsetting the adverse effect of fluctuating demand because there is a fluctuation of demand. So we are offsetting that. Assure steady output from existing plant. So yeah, so we are making we are operating our plant on a fixed optimized capacity so that a steady output from the existing plant can be considered. Meet peak demand on short notice. Suppose suddenly the demand is increased. So what we can do, we can use the energy storage to supply the increased demand and to meet the peak demand on very short notice. So all three options are correct. So correct options are A, B, and C. So D is the correct answer, all of the above. So let's come to the question number 2. What kind of turbine is used in pumped hydro storage system? So I think we have covered pumped hydro storage system. So in this system, what kind of turbine we use? Go through all the option and let me know the answer. So basically let me give you a hint for this question. So we are talking about pumped hydro storage system. So in this system, so basically we are having some elevation, okay? And we are having turbine here. So basically we are using this we are using the water stored at high elevation to drive the turbine and to generate the power. But if the demand is not so high, we are pumping back the water to this head, and during the peak demand, we are again running this turbine. Okay. So what kind of this turbine should be? That is the question. So what kind of turbine is used in pumped hydro storage system? So we have option like Pelton, Francis, Rose flow turbine. So let me give you another hint. So I think this turbine should be like this so that during the peak demand time, it can work as a turbine, okay, or during normal operation, it can work as a turbine. And during like we are not having enough demand, okay, so during that time, it can work as a pump so that it can supply back this lower level water to a higher level. So what kind of turbine we have to use it?
So Francis turbine, sir.
Yeah,
It both pump. It will pump and also work as turbine.
yes, correct. So the correct answer is option B, Francis turbine, because the Francis turbine is work on the principle of both reaction turbine and axial turbine. So it can do both. So Francis turbine act both as pump to pump the liquid up in off-peak hours and turbine to generate extra electricity in peak hours. And normally we use Francis turbine. It is having very high efficiency up to 90%. Okay. It is basically an inward flow reaction turbine that combines radial and axial flow concepts. It's important. It is Francis turbine. Question number 3. The compressed air entering to the reservoir in CAES. Okay. So compressed air energy storage system has space pressure and space temperature. So when the compressed air is entering into the reservoir in CAES, like what about the pressure and temperature? Should be high, low, high, high, or low. So let me give you a hint like in CAES, we are using compressor and we are also using heat exchangers. So maybe you can think that if we are using compressor, then what is the effect of the compressor on the pressure and temperature? And when we are using the heat exchanger, then what is the effect on pressure and temperature? So maybe you can try to recall the class notes and you can answer this question. Let's take one more minute. Let me know the answer. So any ideas, Hawaz?
Sir, for compression, high pressure is required, sir, and heat exchanger has a low temperature, sir. So I think answer is high low, sir.
Okay. Let's see. So yeah, correct option is option B. Because in compressed air energy storage system, CAES, air pressure is high as it is passed through the compressor. So actually we are compressing the air, okay, and we are storing it at high pressure. So that after some time we can use this to run the turbine. So the pressure is high, but we don't want to store it at high temperature. Okay, so what we do? So we pass this through the heat exchanger. Okay, so the temperature is low after it passes through the heat exchanger before entering the reservoir. So basically, we are storing the gas, storing the air at high pressure and low temperature. So the correct option is option B. Okay. So in compressed air entering to the reservoir in CAES has high pressure and low temperature. What kind of heat exchanger is used in CAES? So as in previous question, we have seen that we are doing some, we are applying a heat exchanger to cool down the incoming air to the reservoir. Okay. So what kind of heat exchanger is used in CAES? Is it regenerative, or is it recuperative or cross flow or none of the above? Let me know the answer. So let me give you a hint. So suppose this is our reservoir, okay, and we are storing air inside it. So in between we are applying the heat exchanger, okay. So this is incoming air and this is outgoing air. So incoming air, so as in our previous question, we have seen that we are compressing it and cooling it to store in the reservoir. And when we need it, so we supply it and we are heating through this heat exchanger. Okay. So what kind of this heat exchanger should be so that it can store the energy when this incoming air is having high temperature and putting it to low temperature, and then when it is going back, then it is again giving the heat to this low temperature air and making it to high temperature. So what kind of heat exchanger is it? Is it regenerative, recuperative, or cross flow, or none of the above? That is the question.
Regenerative, sir.
Regenerative. Okay. And what is the reasoning behind this, Shahbaz?
Sir, Sir, high temperature is there, no, sir. Hot
Okay.
fluid is intermediately stored in a thermal storage, sir. Hot
Okay.
fluid, hot fluid. So before it is transferred to cold. So regenerative is done by this process, sir.
Okay. Yeah. Basically, in regenerative heating, we are having only one stream passing at a time. Okay. Suppose this is a heat exchanger. So suppose this is the stream. Okay. So at a time, only one stream will pass through it. Okay. So suppose this time the heated stream that was incoming air. Okay. Okay. So incoming air. So this incoming air is suppose 800 degrees centigrade. Now in this regenerative heat exchanger, it will lose heats, and this regenerative heat exchanger having some packings. Okay. It is different kind of like some maybe oil, some packing, or some other things. Okay. So that this high temperature air will give heat to this packing material or the material that is filled in this heat exchanger. Okay. And cool down to maybe 150 degree, 100 degree. It depend on the heat exchanger. Okay. So now this packing, it is insulated from outside, and this packing material is having the heat that was initially with the incoming air. Now when we supply the cold air from this side, okay, so what this heat exchanger will do? It will supply the stored energy to this air and heat it. Suppose it will be at 150 degree, so it will heat it again to 800 degree centigrade. So basically, it is regenerating the heat. First, it is storing the heat, then it is giving it back to the air. So this is called regenerative heating. Okay. So in recuperative, both streams are flowing simultaneously. Okay. Together, they are exchanging heat in between. Not like in this regenerative. Okay. So the correct answer is option A, regenerative heating. So there's a numerical. Nice. So to store 0.49 megajoule of energy by 500 kg of water, what should be the height to which the water should be pumped? Assume no pumping loss, density of water, and con and the gravity constant G, 9.81 meter per second square. So what should be the height to which the water should be pumped? You've given the energy, you've given the mass of water, you've given the density, you have given the G. Okay. So suppose this is the reservoir. We are pumping water from this height to this height. So you have to calculate this H. Take 2-3 minutes and let me know the answer.
Sir, 99.89 meters, sir. D, sir, answer. 100 meters.
Okay. So let's
D.
wait for another 1 or 2 minutes. Maybe those who will be taking this class online, they're also trying to solve it. So let me give you a hint. So basically, the stored energy can be found out.
Potential energy is equal to mgh, sir.
Yeah, yeah. So it will be potential energy, that will be mgh. So you have m, you have g, you have h. Also h you have to find out. You have q. So put all the data and now try. Okay. So the energy stored will be mgh. So we have it will be h will be energy stored upon mg. Okay. So we have stored energy as we have given 0.49 megajoule. So always be aware with units. So you have given megajoules. Okay. So first convert it into joule. So multiply it with 10 raised to power 6. Okay. It will be 0.49 into 10 raised to power 6 joule upon mg. Mass should be in kg. So it is 500 kg into g in meter per second square, 9.81 meter per second square. So when you solve it, you will get 99.89 meter. And now check the option for nearest answer. It will be D. Okay, 100 meter. So the correct option is D. Option number 6. Again, compressed air energy storage stores energy in the form of space energy, while flywheel stores energy in the form of space energy. So we have studied two different types of storage system, energy storage system. Okay, one was CAES, compressed air energy storage, and another was flywheel. So what kind of energy we are storing? That is the question. So take 1 or 2 minutes and let me know the answer. Any answer, Sehbaz?
Sir, flywheel kinetic energy, sir. Energy stored as a kinetic energy in a rotating hub in a flywheel, sir.
Okay.
And
So
and compressed air means pressure energy, sir. There is air is pressurized. So pressure
yes,
energy.
correct, correct. So the correct answer is A. Compress air energy storage. So as name suggests, compress air. So we are basically compressing the air. We are storing the compressed air. Okay. So basically, when we are compressing it, it means that we are raising its pressure. Okay. So the compressed air energy storage system compresses the air and stores energy in the form of potential energy. Okay. So we are increasing its pressure. On the other hand, the flywheel, which stores in the energy in the form of kinetic energy. So basically, we are rotating, okay, and due to rotation and weight, we are storing the kinetic energy in the flywheel. Okay, so the energy storage in the form of pressure energy, while flywheel stores energy in the form of kinetic energy. So the correct answer is option A. Which of the following order is correct variation of current in charging, storage, and discharging stage of an SMES? Linearly increase, constant, linearly decrease, linearly increase, linearly decrease, constant, C, linearly increase, exponential decrease, linearly increase, constant, and exponential decrease. Take 2-3 minutes and let me know the answer. So SMES storage is superconducting magnetic energy storage. SMES, superconducting magnetic energy storage. Try to recall this and let me know the answer. So basically in SMES, we store energy in the magnetic field created by the flow of direct current in a superconducting coil, which has been cryogenically cooled to a temperature below its superconducting critical temperature. So try to recall this and let me know like what is the correct variation of current in charging, storage, and discharging. So like when we are doing charging, it means that current should increase that time. Storage, so basically current will be constant, and discharging then current will be decreasing. But what kind of, like it will be linear increase or linear decrease? That is to that is the main question. I think let me remind you a graph. So in this one is increase, two is constant, and three is decrease. So one is charging, two is storage, and three is discharging. Now I think you can Decide the answer.
Sir, answer is D, sir. That sir told in the class. Linearly
Yeah,
increasing when charging and storage is constant. Discharging is exponentially decreasing.
yes, yes. So you can see from the graph also. So it is
So,
linearly increasing in one. So the charging is linearly increase. Then the storage is constant, and then during discharging, it is decreasing as exponentially. Okay, it's exponentially decrease. So the correct answer is answer D. Question number 8. In pressurized water storage, TES, how many turbines are used during peak hours and off-peak hours? So in pressurized water storage, TES, how many turbines we are using? That is the answer. During peak hours and off-peak hours. So T is basically thermal energy storage. So in pressurized water storage, thermal energy storage, how many turbines are used during peak hours and off-peak hours? Okay, let's see. So the correct answer is option D. 2 during peak hours and 1 during off-peak hours, because in pressurized water storage, TS, a single turbine is used in off-peak hours where a portion of the steam is sent to the accumulator. In peak hours, using another turbine, the power is extracted from the accumulator. Okay. So in peak hours, we are extracting the power from the accumulator in where some steam is stored already. Okay. So that in peak hours, we need two turbines, and during off-peak hours, we need only one turbine. So the correct answer is option D. In compressed air storage plant, air is compressed from 1 bar 25 degrees centigrade to 50 bar. Calculate the compressed air temperature, assuming Cp to Cv ratio of air to be 1.4. A basic thermodynamic question. You have to find out the temperature after compression. You have given that all conditions. You have to apply the relation between pressure and temperature. Try to find the relation and let me know the answer.
six 38.24 degrees centigrade.
Okay, nice. Let's wait for another 1 or 2 minutes. So let me give you a hint. The relation between the temperature and pressure is T2 upon T1 equals to P2 upon P1 to the power gamma minus 1 upon gamma. And gamma is the ratio of specific heat, Cp upon Cv, that is given 1.4. Now, an important point is that in this relation, the temperature is in Kelvin. That is very important. Okay, because if you put the temperature in degree centigrade, then the answer will be wrong. Okay, so the temperature is in Kelvin. Now try to calculate the answer. Actually, the yeah, yes, Abaj,
Yes, sir.
yeah,
638.24 degrees centigrade.
638. Yeah, correct. So when you put this data, so it will be like T2 upon T1 will be 25 plus 273 equals to, so P2 is 50 upon 1 bar, 50 bar. Okay, 1.4 minus 1 upon 1.4. That will give you the T2 equals to 911 Kelvin. So now converted into degree centigrade, it will be 638 degrees centigrade. So nearest answer is 640. So the correct option is option D. Question number 10. If in previous problem 10, if the compressor efficiency is 90%, so you have given the compressor efficiency is 90%, what should be the compressed air temperature? So this relation is for isentropic. Okay, if the condition is isentropic compression, then this condition follows. But now you have given the efficiency of compressor. Now, what will be the correct outlet temperature? Okay, what should be the compressed air temperature? Means what will be the correct T2? The previous T2 is, you can say T2S, that is for isentropic condition. But now you have to find out the correct T2 based on this compressor efficiency. Let me know the answer.
Seven not 6 degrees centigrade.
Sorry,
706 degrees centigrade. 706.1.
706.
6.
Okay, just wait for 1 or 2 minutes. Okay, so this is the relation for the efficiency. Okay, so it will be 0.9 first of all, because you have given 90% efficiency. So T2S minus T1 upon T2 dash minus T1 equals to 0.90. So the isentropic we have calculated as 640. So based on this, T1 you have already have, T2S you have. So this will be T2 dash. So you will calculate, it will come to the 706, right, Sebas?
Yes, sir.
Okay. So the nearest option is 700 degrees centigrade. The correct answer is 700. The next question is, what is the main objective of energy storage? I think we've already covered it. So basically, the correct answer is all of the above, because we want to offset adverse effect of fluctuating demand. We want to assure steady output from existing plant, and we want to meet peak demand on the short notice. The next question is, in pumped hydro system, which is not a source of loss? So which one is not a source of loss? So A is leakage of fluid from pipes and equipment, water addition due to rain, evaporation during storage, and turbine losses. What is the correct answer? Let me know. So I think you have to just think about it, like in pumped hydro system,
Sir,
fuel is
option A
not a
is
source.
option
Okay,
A is
option
okay.
leakage of fluid from pipes and equipment. No, you have to think about it, because this is the main reason of losses. If your fluid, if your water is leaking from the pipes and equipment, and suppose your pipe is pressurized, so suppose your this is the pipe, okay? It is pressurized maybe up to for 20 bar. If there is a leakage, then this pressure will come down.
Sir,
So there is a huge loss
sir,
due to this.
water addition due to rain, sir. This is not known.
Yeah, yeah, correct. So suppose in a energy hydro energy storage system, this is the case. Okay, we are storing water at high elevation. So if raining is there, so it's good actually. We don't have to fill this; it automatically filling. It's good. There is no loss. Actually, it's providing more water, so we can generate more energy. Okay. So water addition due to rain is not a loss. It's a good thing. So this is the answer. Evaporation during storage is also a loss. Turbine losses also a source of loss. Okay. So the correct answer is B. Water addition due to rain is not a loss. Okay. Number 3. Why is the compressed air in a storage system cooled before storage? A. Prevent heat loss during storage. B. Improve turnaround efficiency. C. Reduces storage volume. D. Help in a hybrid system. So let me know the answer. What is the reason behind it? Why we
Sir,
want to cool it?
reduces storage volume, sir.
To reduce the storage
Volume.
volume. Okay. What is the reason? Like,
Sir, if it is heated means it will take more volume, sir.
okay, if it cooled, then volume will become
Reduce.
less. Okay. So the correct answer is option C. Because the temperature is high, it means that volume is also high. So we want to reduce the storage volume because we are storing the compressed air. If it require more volume, then it will be going to difficult because we will require more space. Okay, we will require more material. So what do we want? So we want to reduce the volume. Okay, so that we can store more air in less volume. That's why we reduce the temperature, okay, to reduce the storage volume. How much energy can be stored by 500 kg of water raised by 100 meter in pumped hydro installation? Assume no pumping loss, density of water to be 1000 kg per meter cube, and G equals to 9.81. I think similar kind of question we have already covered. Try this one also. Take 3 to 4 minutes. Point to be remember, options are given in megajoule and kilowatt hour. I suggest whatever your answer first in maybe in megajoule, then try to convert that in kilowatt hour and check all options.
Sir, BD.
B and D. Okay. Wait for 1 more minutes. After that, we will discuss it. Okay. Let me know the answer, Shahbaz. So what is the
MGH.
concept?
Potential
Energy stored is
MGH.
mgh. So what is the m? M is
And
given 500 kg. G is 9.81 meter per second square, and H is I think 100 meter. What is the answer?
0.49 megajoule.
49 megajoule. Okay. So nearest option is 0.5 megajoule. Now we have to convert this megajoule into kilowatt hour. How to convert it, Seba?
Divided by 3600, sir.
0.49 divided by 3000.
600. 8 to
600.
10 to certain to power of 6, 0.4.
Yeah, because it's mega joule. So it will be in kilowatt hour or directly in watt hour?
Watt hours at 136.25 watt hours.
136.25
25 watt hour.
watt hour. So now see the options. So in kilowatt hour, it will be 0.136. Okay, so nearest option is 0.15 kilowatt hour. So the correct answers are B and D. Okay, so the options are B and D. Okay. So in an SMES, option A, magnetic energy is converted to electrical energy. Magnetic energy can be stored indefinitely. Electrical resistance of the coil drops to zero. And D, all of the above. It's superconducting magnetic energy storage system. Okay. So what are the options?
Sir, D, sir.
Okay, Sabaj, let's wait for 1 minute. After that, we will see. Okay. So the correct answer is D, because in SMES, magnetic energy is converted into electrical energy. That is correct. Magnetic energy can be stored. We are storing it, and electrical resistance of the coils drops to zero. Yeah, it's also correct. So the options is option, all the A, B, C are correct. The correct answer is option D, all of the above. A flywheel's energy storage can be increased by locating more mass at the circumference, reducing friction losses, and choosing material with high tensile strength. D, all of the above. Try to think about it. Try to recall the formula of flywheel's kinetic energy and let me know the answer. Any answer, Sahbaz?
Sir, all the above, sir. All are
Okay, and what
necessary.
is all of the above? So let me know the reasonings.
Sir, if you increase the mass, the form in the formula, sir, mass rate increases, energy storage increases, sir.
What is the formula for flywheel's energy?
Sir, I is equal delta E is equal to I half into I into omega 1 minus omega 2 minus omega 1 square or omega square, sir. Omega 2 minus
Okay, this is the energy stored. Okay, so basically the
omega 2.
energy is half I omega square. Okay,
Yes, sir.
so this is the basically energy at particular RPM. Okay, so you can see the I is the moment of inertia. So what is the moment of inertia of a disk?
Half ml square,
So it will be
mr
I
square,
equals to half
mr square, mr square.
mr square. Here m is the mass, r is the radius. So we can say that energy is proportional to mass of the flywheel. Energy proportional to radius of the flywheel. Okay, so now see the option. Locating more mass at the circumference. So what does it mean? Circumference mean we are increasing the r. Okay, and we are locating more mass at circumference. So we are basically increasing the m also. So we are both increasing r, we are increasing m. So we are increasing I. If I is increased, then means E is increased. So correct. Reducing the frictional losses. So if we reduce the friction losses, then automatically the energy storage will be increased because due to the friction, the flywheel comes to rest. But if we are decrease the friction losses, then it can have more RPM. So B is also correct. Choosing material with high tensile strength. If material is have high tensile strength, then what will happen, Sabaj?
Is good, sir. High energy can be stored. Life of the flywheel can be increased, sir. Life
Life of the flywheel will increase. Okay, it will store more energy. It
energy.
can last up to more time. So choosing material with high tensile strength is also important. So correct answer is B. All of the above. So number 7. What is the primary reason for the Alabama CAS compressed air energy storage installation more energy efficient than Contour installation? So I think we have covered two types of installation in the class. So what is the more reason behind that? That the Alabama CIS is more efficient than the Hunter installation. So option A, recuperator uses waste heat from turbine. B, newer plant with better equipment. C, hybrid system with adiabatic storage. D, uses intercooler between compression stages. So try to recall about class notes and let me know the answer. Any answer, Shahbaz?
Sir, answer A, sir. Recuperator uses waste heat from the turbine, sir. It is in
Okay.
Alabama, sir. Alabama, it is there, sir. Point.
Okay. So the correct answer is option A, because in Alabama installation we are using a recuperator to use the waste heat from turbine. Okay, that's why it's having more energy efficient. So the correct answer is A. Okay. Question number 8. So very important question. A flywheel in the form of a disc, diameter 5 meter and thickness 2 meter, rotates at n equals to 3000 rpm. It is made of a material with uniform density of 2000 kg per meter cube. Calculate the energy stored in the flywheel. So take 3 to 4 minutes and let me know the answer. Be careful with the units. Okay.
Sir, 12 gigajoule, sir.
How much?
12 gigajoule.
12 gigajoule.
Yes, sir.
Okay. So the formula for stored energy is E equals to half I omega square. Okay. So the I is mass moment of inertia. I is half m r square. So we have given diameter D equals to 2 meter. Sorry, diameter is 5 meter. So R will be 5 by 2 or 2.5 meter. What about the mass? The mass of flywheel will be volume.
To density.
Sorry,
Volume into density, sir.
volume into
Density.
density.
Low.
So we have given 2000 kg per meter cube. What about the volume? So volume will be area into thickness. So area will be
5/4.
pi by 4 d square into T into rho. So the mass will be pi by 4 d, it's 5 to the square. Thickness is 2 meter into rho is 2000 kg meter cube. 2000. So what is the mass? Sebas? Sebas? What is the mass?
Sir,
So what is the solution of this mass?
sir, 778,539
78539.81
0.81 kgs.
kg. So we have mass now. Okay. So calculate the moment of inertia I equals to half this 78539.81 multiplied by R is 2.5 square. So you will get I. Okay. So put I here. Now omega is 2 pi n by 60. Okay. So you have n is RPM. So put omega value, then put omega square. After solving the whole calculation, you will get the stored energy in the flywheel is 12 gigajoule. So the correct answer is 12 gigajoule. Very important question. Okay. So the main point is that you should know what is the mass moment of inertia of the disk. Okay. And always be careful with the units. That's very important. Okay. So let's move to the next question. So if the flywheel in previous question is lower down to 1500 RPM, initially the RPM was 3000. Now the RPM slowed down to 1500 RPM. So how much energy can be recovered? Now let me know the answer.
Sir, 9 gigajoules.
9 gigajoule. Okay, let's wait for another 2 minutes. After that, we will discuss. So what is the formula, Shahbaz, now?
Sir, delta E is equal to half into I into omega 2 square minus omega 1 square. I into bracket omega 2 square minus omega 1 square.
Okay. So I think it will be omega 1 minus omega 2, I think.
Yes, sir.
Yeah. Because otherwise this quantity will come negative.
Okay, sir. Sorry, sir.
Omega 1 minus omega
2
2.
square.
So
Omega 1
it
square.
will be omega 1 will be
2
omega
pi
1
n
is 2 pi
pi n
n1 upon 60,
60.
and omega 2 is 2 pi n2 upon 60. And n1 is the initial RPM is 3000 RPM, and n2 is the final RPM, that is 1500 RPM. Okay. So put all the value, you will find the energy that can be recovered, that will be 9 gigajoule. Okay. So next question. In a CAS plant, air is compressed to 1 bar, 25 degree to 50 bar. I think we have already covered this question.
Repeated question.
So repeated question. So it is
6 repeated.
first T2 upon T1 equals to T2 upon P1 to the power gamma 1 upon gamma. Okay. So in previous question, the compressed efficiency, okay, we have also done this. Okay. So these were the questions for today. Now let's revise some theoretical concept now. So basically about energy storage. So it's about electrical utility system. So we can have variable demand, but we can have fixed supply. So variable demand is due to hourly or and even season to season. So this result in large expensive plant mostly operating below capacity. So we have already discussed it that we don't want to operate our plant at below capacity because this will lead to low efficiency, more emissions, higher operating cost. Okay. So we will apply the energy storage system. So it will do like it will generate the extra energy during less demand and store that energy, and during the peak demand we will supply this stored energy. So it will meet the fluctuation in electricity demand and assure a steady supply economically. Okay. So plant is continuously operated in base load mode. So if demand is less than capacity, then what is the excess energy is stored. If demand is more than capacity, then what is there? Stored energy is released. So very important points. So it depends on the demand and capacity. So this is a simple curve, like from early morning, from night 12 a.m. to midnight. So you can see the demand is very less up to morning 6 a.m. Okay, after that demand start increasing. Then during the daytime, demand is almost constant, and during after office hours, you can say, or after uh, around 7 p.m., the demand is again decreasing. So in this way, this is the load curve. So we have to design our system so that we can meet all these criteria. So we have different types of storage system like mechanical, electrochemical, magnetic, thermal, and chemical energy storage. In mechanical, we have three types: pumped hydroelectric storage, compressed air storage, and flywheels. So in pumped hydroelectric, we have already covered. We are storing water at high level reservoir. Okay. Then there is a station, or you can say a turbine. It is generating the power. So water pumped into a high reservoir during off-peak hours. So during off-peak hours, we will pump back this water to this reservoir. During high demand, water flows down. So during the high demand, The water flows down to the turbine and power and water flows down and power the reverse turbine. So it will power the reverse turbine used for load balancing of energy. In this way, we can balance the load. So this turbine, suppose basically this one power goes to consumer. Okay, if excess power, then surplus power, then we will apply this power to raise this water from at a lower level to higher level. If the peak demand, okay, this is the night time, this is the daytime. So daytime we have peak demand, so water, the power is going to consumer, we require more power. So again, this high, the water stored at high level is again driving the turbine and generating more power. So we are getting power from here. We are getting more power and that can supply to consumer. In this way, we can fulfill our demand and supply. So advantages are like mature and reliable technology. It's very mature. Hundreds of plants around the world. US has around 9.5 gigawatt of capacity. Okay, 2.5% of base load. High overall efficiency, like 70 to 80% is the efficiency. And fast response time. Response time is also very fast. It's also some disadvantages. Limited potential sites, need for high altitude reservoir. Sites are limited, okay, because we need high altitude reservoirs. Environmental and political factors, they are also concerned. So these are just a curve showing the installation capacity. So in India, we are having these locations in Andhra Pradesh, Maharashtra, Tamil Nadu, Gujarat, Jharkhand, Madhya Pradesh, Maharashtra, okay. And the recent one is Uttarakhand, Tehri, okay, near Haridwar. So it is capacity of 4 crores to 50 megawatt. So about to 2018 is it expected. So these are again some examples. Now compressed air energy storage. So here we are storing the energy, okay. So we are compressing the air and supplying it to the compressed air stores, okay. Here the heat exchanger that we have already discussed. And during the, this is the like off peak, okay. So basically we are storing here, okay. So the energy generation is more than the demand. So we are storing, we are compressing the air. The air is coming in the reservoir. Now the demand is more, then we are running this turbine and generating the power and supplying it to the main grid. This is the loop, okay. So during off peak, excess electrical energy is drive and air compressor. Compressed air stored in an underground reservoir or aquifers or caverns. Then during peak time, compressed air used to drive an air turbine coupled to a generator and delivers electricity. So advantages are like high storage capacity, similar to pumped hydro, high overall efficiency, 7 to 20%, fast response time, and inexpensive. Also, some disadvantages like require large storage reservoir, storage limited to a day or for adiabatic system and not matured yet, and competing against other storage needs. Now, there's two types of compressed air energy storage: adiabatic and diabatic. So in adiabatic, heat from the compression is captured and stored in a solid or liquid form like packed bed, hot oil, and molten salt. Heat is reincorporated during release and it's close to 100% efficiency. In diabatic storage, heat is lost through cooling. Natural gas is burned to reheat compressed air. It is inefficient and use half gas of an all gas plant. So this is the installation of Hunthorpe. I think we had also a question about this. It's world first CIS plant, two mine salt caverns with total volume of 300,000 meter cube, a depth of 600 meter, hybrid variety heat addition prior to GT using natural gas as a fuel, and storage occurs daily for 8 hours at the 60 megawatt and generation for 2 hours at the 290 megawatt and uses zero point 0.8 kilowatt hour of electricity and 1.6 kilowatt hour of gas to produce 1 kilowatt hour of electricity. On the other side, there is a Alabama system, 1991. It stores compressed air up to 7.5 megapascal in an underground cavern in mine salt dome, 250 meter below the surface. Storage capacity is 500,000 meter cube. Generating capacity of 1110 megawatt over 26 hours. Natural gas heats air before expansion in turbine. Recuperators reuse heat energy from the gas turbine. So this is the point. I think we had also a question about this. Recuperators are used in Alabama plant. It uses 0.69 kilowatt hour electricity and 1.17 kilowatt hour of gas to produce 1 kilowatt hour of electricity. So basically 25% less compared to the Hunthorpe CS plant. It is more efficient due to these recuperators. There's another plant in Texas. No fuel is used there. Okay, several other commissioned or underdeveloped plants are there. Now flywheel. So flywheel basically stores kinetic energy, okay? And it stores a kinetic energy rotating hub. The formula is half I omega square. Important, okay? For cylinder, the moment of inertia is half mr square. For high energy, increase omega, yeah, either increase the RPM, okay, or increase I, increase the moment of inertia by locating more mass towards the circumference. Use materials with lighter mass and high tensile strength like carbon fiber, reinforced material. Stored energy will be like calculation delta E 2 pi square mr square n2 square minus n1 square. So maximum energy density is related to the maximum tensile strength, okay? So about construction, then materials, spinning rotor, steel or carbon composite. Steel rotors can spin at 7,000 RPM and carbon composite spin up to 6,000 RPM. 60,000 RPM, sorry. Bearing, mechanical bearing, not practical. So friction directly proportional to speed. Magnetic bearings used to minimize friction, like magnetic levitation. I think their trains are also working on this principle, magnetic levitation. Operates in a vacuum reduced air friction. So what are the pros of flywheels? Low maintenance and long lifespan, up to 20 years. Zero carbon emission, fast response time. Okay. Also have some disadvantages like expensive, low storage capacity, and self-discharge. So these are only for, you can say, for fast response time. Okay. Like to maintain the speed and to maintain the energy and for only like for a moment. Okay. Not for longer duration. Expensive, low storage capacity, and self-discharge. Now, superconducting magnetic energy storage SMES. So this is the basic diagram. SMES system stores energy in form of an electromagnetic field surrounding the coil. Okay. This is power system, suppose, and power conditioning system. Then this is the coil, and there is a system. Okay. Superconducting magnetic coil below critical temperature is used to store energy. So below critical temperature is used to store energy. Charged by a DC supply till threshold current is reached. So it is charged by a DC supply. Circuit shortened. Thereafter, current continues to flow without decay. So we short the circuit. So the current flows without decay. Discharge happens on reverse flow polarity. To discharge, we have to reverse the polarity. Now, power electronic circuit for AD conversion, varying voltage and reversal of polarity. Varying magnetic field during discharge is potential hazard. It would because wound coils used for smaller energy storage, like short-term requirement for stabilizing, and larger systems use a toroidal structure. Stable construction withstand mechanical forces. Material like low TC material, molybdenum, titanium, and high TC material, yttrium, barium, copper oxide. Now the thermal energy storage TES. So the TES, like very technology possible, allows excess thermal energy to be collected for later use. So in this, we are collecting thermal energy like for hours, for days, or many months later. Summer heat from solar collectors stored interseasonally for use in winter. So we can store the heat available in summer to use it in winter. Cold obtained from winter air can be provided for summer air conditioning. So we can use the obtained during winter for summer air conditioning. So sensible heat storage system. So basically we are using sensible heat storage. Use high thermal mass. So density and specific heat should be more. So it's rho Cp. Rho Cp should be high. So the examples are pressurized water storage, packed beds, organic liquids, or fluidized solid beds. So we can store the sensible heat source can be pressurized water storage, packed beds, and organic liquids, and fluidized solid beds. And latent heat storage are uses heat of fusion. They can be ice storage, phase change materials like organic alkanes or hydrate salts and molten salts. So during off-peak, more steam produced at HRSG and excess steam bleed from the turbine at high pressure. Okay, fed to steam accumulators to produce saturated pressurized water. And during peak time, the accumulators discharge water flushes due to decrease in the pressure. So because the water was stored at high pressure, now the pressure was released, so it will directly flushes into the vapors and expands in peaking turbine to generate electricity. So this is the kind of system. So I think that's enough for today, but still we have some time left. So I will move from again question 1. If anybody is having any doubt, let me know. We will discuss that again. Anybody has any doubt, let me know. Any doubts, Abbas, in any question?
Sir, no doubt, sir.
Okay.
చేశాను రెండు క్వశ్చన్లు చేయాలి. ఏం బెండకాయలు ఉప్పే లేదు.
Sabaz, your microphone is on. I think you can turn off if you're not speaking. So I think there is no doubt. So we have covered around 22 questions today, and we
Yes,
have
sir.
also covered uh, some concepts from previous week class. So I hope you have learned a lot about the question and the concepts. And I hope next week also many of you will join the session. Those who are not joining today, I hope you will be available in the next session. That will be on next Friday, 7 to 9 p.m. So please join the session, because if you are having discussion, then it's a very good thing, because so that more doubts will be clear, more new can say new thoughts will become regarding the questions. Okay, we have more ways to solve. So I hope everyone will join the session, and we will have a very good discussion in next class. I think it's a very good session today. So thank you everyone. Thank you for joining.
Thank you. Thank you, sir.
Okay, thank you. So I am ending the meeting. Thank you.